Okay, section 5.5 complex eigenvalues. Before we work on complex eigenvalues, if you don't mind, I just want to quickly review and remind you some properties of complex numbers. I'm sure you have done this in your high school, and if you remember all of the properties that you learned in high school about complex number, great. If not, then I'll take maybe 5 to 10 minutes to quickly remind you all of these properties of complex numbers. Okay, first of all, there are the real numbers. For example, if you have x squared minus 1 equal to 0, and if you solve this equation, you're going to get x equals plus minus 1, which is real numbers, okay, real values. And if you want to solve x squared plus 1 equal to 0, then you'll get x squared equals minus 1. So x squared equals plus minus minus 1, right? Let me ask you one thing. Negative, 4 square root 4. Can you tell me what is the value of that?
2 plus minus 2.
Plus minus 2.
Plus minus 2?
It's just 2.
Just 2, yes. Keep that in mind, it's just 2. Now, when x squared equals 4, and then if you have x equals plus minus square root 4, then it will be plus minus 2. See the difference, okay? When you do the square root, then you will write plus minus square root 4. So plus minus comes as it is, and square root 4 is actually 2. So just keep that in mind. Now in this case, x squared equals negative 1. So x equals plus minus square root negative 1. And negative 1 is defined to, square root of negative 1. There is no real number for that. So negative 1 is defined to be I square. Okay, so what we do is plus minus, this one is I square. So negative 1 is I square. So you're going to get I square. Okay, so that means plus minus I. Just keep that in mind. Negative 1 is I square. That's how we define. I means imaginary number.
Professor,
Yes.
can we prove in another method, like we put square root minus 1 is equal to I. Then after that we are going to squaring both sides. Then it is equal to iota square is equal to minus 1.
Yeah, you can do that. No problem. Yeah, it's the same idea. But, we define this, I square is defined to be minus 1. That is how we defined the imaginary number.
Yeah.
Definition. So it doesn't require any proof. Okay. Now, let z equals a plus bi be a complex number where I square equals minus 1 is the imaginary number. Then z belongs to, complex number, the set of complex numbers. Then in this case, the real part is a. Okay, z is a plus bi. This a is called the real part, and then the second one, this b, is called the imaginary part of z. Okay, and another concept, another word that you should know is complex conjugate. What that means is, suppose z equals 3 minus 7i, then z bar, which is, that's how we represent
Plus
the,
7I.
yes, 3 plus 7i, just the opposite sign here. Okay, opposite sign between this real part and imaginary part, just in front of the imaginary part, in another word. So if z equals 4i, then your z bar, which is actually the conjugate, complex conjugate, will be negative 4i, because z 4i means you can write this as 0 plus 4i. Okay, so that means you'll have 0 minus 4i is the complex conjugate, which is 0 minus 4i will be simply negative 4i. And if z equals 5, it's just a real number, the complex conjugate will be 5 can be written as 5 plus 0i. So complex conjugate will be 5 minus 0i, which means simply 5. Okay, so if z is a real number, then the conjugate will remain the same. There will be no change. All right. Magnitude. So what is magnitude? How do we define magnitude? Well, magnitude is defined to be, suppose z is, if z equals a plus bi, then z bar is defined to a square plus b square. Okay, that's the magnitude. That's how we define. And if I do z minus z bar, so that's going to give me, let me see what that will be. Z is a plus bi, and z bar is a minus bi square root. So let's see, what do we get? If I multiply this, we get a square plus b square I square. Sorry, minus b square I square. Right?
After that, it will become plus.
A square minus b square, I square means minus 1. So that's going to give me a square plus b square. You see, we got the same thing, a square plus b square is square root, and z bar is also a square plus b square is square root. So we can write this as z bar equals z minus z times z prime, square root, and if you square both sides, that's what you're going to get. So we can prove it easily. Okay. And another property, if z and w belongs to the complex number, then z times w always equal to z bar times w bar. That means product of the complex number will be equal to, let me repeat that, product of the complex number will always be equal to product of their conjugate. Okay, keep that in mind. All right. And if we have 1 over I, we can write this as negative I because it's pretty simple, right?
Yeah,
So,
by rationalize.
yes, if you multiply both sides. Okay, now let's look at this example 1. If x equals 3 plus I, find real part of x and imaginary part of x, as well as the conjugate of x. 3 things we want to find, guys. Okay, let's try that. X equals 3 minus I and 2 plus 5i. So I can write this 0 plus I for that if I want. So I can split that into real part, which is 3, 0, and 2, plus I can split the imaginary part, which is negative 1, 1, and 5. Right? So clearly, what is the real part of x?
302.
Thank you. And imaginary part of x is,
15.
thank you. And then what is x bar, which is conjugate?
Yeah, 3 plus I minus I, 2 minus 5i.
Okay, so this will be 302 minus I negative 115, right? Remember,
Can I write it to combine the whole matrix?
yeah, why not? So I'm gonna write, or you can simply say that this will be 3 minus and negative will be positive I, right? And then this will be minus I, negative I, and that will be 2 minus 5i. Yes, you can write this way directly, no problem. Okay. It's just that, the sign for the imaginary part, we change the sign. That's what we call conjugate. We change the sign for the imaginary part. All right, so you know how to find the real part and imaginary part. All right. Okay, so the review part is done. The high school part is done. So I want to bring you back to the college math concept, okay? Complex eigenvalues and associated eigenvectors. Here is the definition. Let A be an n by n matrix with real valued entries. Then a complex valued lambda, which is an eigenvalue, is an eigenvalue of A if there exists a non-zero vector x in Cn, which represent the set of complex numbers. So this is the symbol to represent set of complex numbers, such that Ax equals lambda x. The same definition. The only thing is lambda is complex number. That's it. Then we call lambda a complex eigenvalue and a complex eigenvector corresponding to lambda. X a complex eigenvector corresponding to lambda, okay? And here is one theorem. Let A be an n by n matrix with real valued entries. If lambda is an eigenvalue of A with corresponding eigenvector V, then lambda bar, which is complex conjugate of lambda, is also an eigenvalue of A with corresponding eigenvector V bar. So this theorem, will be applying this theorem in the next problem, but let us prove it quickly, okay? The proof is here. Anyway, we'll do the proof later, but let's work on this example 2 first, and let us learn how to find the eigenvalues and eigenvector, and then we prove that theorem later, okay? Example 2. Let A is a given matrix, which is this 0, 5, 0 and negative 2, 5 and 2. Find the eigenvalues and corresponding basis for the eigenspace. Okay. So first of all, we need to find the characteristics equation, because we need to find the eigenvalues. So consider the characteristics equation. Okay. Characteristics equation, the definition is determinant of A minus lambda I equals 0. So that's the definition. So let us calculate what is A minus lambda I. 0, 5, negative 2, 2, minus lambda 1, 0, 0, 1. So that's going to give me
minus lambda 0 5, sorry, minus 2 minus lambda and 2, no 1.
Yeah, you're right. Thank you. Okay. So what we got here is determinant of that. So determinant of negative lambda 5 and negative 2 and 2 minus lambda equal to 0. Now the determinant, you know how to find the determinant of this 2 by 2. That's pretty simple. Negative this one, 2 minus lambda minus negative 2 and 5 equal to 0. And if you simplify it, what do you get? Let me write it here. So that's going to give me negative
lambda square minus 2 lambda plus 10.
And if you simplify, what do you get?
Plus 10.
Yeah, plus 10 equal to 0. Thank you. It looks like this is not a real number. So I think you cannot factorize it easily, but you know the formula, right?
Yeah, it's a by quadratic formula.
Exactly. So using quadratic formula,
Yeah, I have a calculator, Professor.
Okay, so lambda equals minus b.
Plus minus.
Minus b is 2. It will be negative, negative, positive. So minus negative
Professor, minus 2 times.
plus minus square root. B square means 4 minus 4a.
C 1
And c is 10, right? Remember the formula is ax plus
over 2a.
equal to 0. So x is plus minus, negative b plus minus square root b square minus 4ac over 2a. So we are using that formula, okay? Quadratic formula here. We're using that there. So this over 2a means a is 1, okay? So if you simplify, you will get lambda equals 1 plus minus 3i. Okay, so we got 2 lambda. By the way, if the eigenvalue is a complex number, let's say lambda equals 1 plus 3i, then another eigenvalue must be its complex conjugate. Another eigenvalue must be 1 minus 3i. They always come in pair, guys. I think you learned that in your high school if you have done this complex number. Complex roots always comes in pair. Okay, so
Professor?
yes.
No. Okay, I got it.
Yeah, they always come in pair, okay? All right, so now we got the eigenvalues. Okay, eigenvalues are lambda equals 1 plus 3i. Algebraic multiplicity is 1. And lambda equals 1 minus 3i. Algebraic multiplicity is also 1. Okay. Now maybe if you want, you can write it down as lambda 1 and lambda 2, no problem. But I just write lambda only. All right. Now what we want to do is we need to find the basis for the eigenspace. Okay. So for lambda equals 1 plus 3i, we need to find basis for the eigenspace corresponding to this lambda equals 1 plus 3i. So let us find the basis for the eigenspace. And recall from our previous chapter, previous section, that if lambda equals 1 plus 3i, so by definition, ax equals lambda I, right? So by definition of eigenvalue, lambda is eigenvalue if ax equals lambda I. This gives me a minus lambda I, sorry, lambda x, I mean. Sorry guys, ax equals lambda x. So a minus lambda
I
ax minus lambda x equal to 0.
a
This
minus
gives me a minus lambda I
x is equal to
0. The whole idea is to solve this system, okay? Now we need to solve it. We need to solve this system. It is very similar to what we did earlier. Or maybe to solve this system, I'll just write this one. Now to solve this system, consider augmented matrix. Augmented matrix A minus lambda I and 0. which equals to, now I want you to find what is A minus lambda I. Okay, A minus lambda I equals, A is what is it, 0, 5 and -2 and 2 minus our lambda is 1 plus 3i and 1, 0, 0, 1. Can you help me? What do you get here?
Yeah, minus 3i,
Okay, minus 1 minus 3i,
5
5,
minus 2, and 1 minus 3i.
yeah. Okay, this is our A minus lambda I. So that means our augmented matrix is going to be minus 3 minus 1 minus 3i and 5, -2, 1 minus 3i and 0, 0. So this is our augmented matrix. Okay, now you can change it into echelon form. Okay, change into echelon form. But you know, especially when we have this complex number, changing into echelon form is not fun, guys, in general. Okay, it involves a lot of calculation of complex numbers, and which is not easy. So what I do is, for this problem I will use a different technique. Maybe we'll do by two methods. So method one, I will say, because reducing to echelon form or row reduction of matrix involving complex number, matrix involving complex number is not easy, quite unpleasant. Okay, it's quite unpleasant. Because as it involves, oh, I already wrote that, unpleasant. So we want to use another easy method. Okay, so what is that easy method? Let me show you this. This, you know, this system of equation, what it necessarily mean is that if you are given, let's say x1, I mean, let's say 2, 3, 5, 1, 0, 0. If you are given this augmented matrix, what does that mean? This means we can write this as 2x1 plus 3x2 equal to 0 and 5x1 plus 3x2 equal to 0. Is that right?
Yeah.
So yeah, so what we do is I do the same thing here. So I'll write -1 minus 3i x1 plus 5x2 equal to 0. Okay, this is x1, this is x2. This is my equation 1. And another is -2x1 plus 1 minus 3i x2 equal to 0. This is my equation 2. And by the way, if you solve this system here, which you already done in high school, whatever value you get for x1 and x2, they must satisfy both of these equations. Is that right? Okay. So it doesn't matter whether you consider this equation or this equation, the value must be satisfied by both of these. So for that reason, I can, you know, the value given by the one equation or the first equation or the second equation will be the same. That's what I'm trying to say. Okay. All right. Here, we know that equation 1 and 2 both represent the same relationship between x1 and x2. Both represent the same relationship between x1 and x2. So we can consider any one of these because we want to see the relationship between x1 and x2. So choose either one, equation 1 or equation 2, doesn't matter. But for simplicity, so we can consider either of the equation for our calculation, but for simplicity, I consider 2, but you can consider equation 1 as well if you want, okay? I consider equation 2. So that means negative 2x1 plus 1 minus 3ix2 equal to 0. So I can write this as x1 equals, can you help me? What do I get x1? X1 will be 1 minus 3i over 2 x2, right? Okay, so I can write x as x1, x2, which means 1 minus 3i over 2 x2 and x2, which gives me, if I take x2 here, I'm going to get 1 minus 3i over 2, 1 minus 3i over 2, and then 1. Okay, this is our vector. But since I don't like this fraction, okay, I don't like that fraction here in the vector. So what I want to do is I can write 2x2. I just want to scale by factor 2 so that I can write 1 minus 3i and then 2. Okay, scaling by factor of, you don't have to, but it looks a little ugly, you know, it's a complex number itself is not, it's you know, complex numbers with fraction, I don't like that. So scaling by factor 2 by factor 2.
Why is it 2, not half?
I need to multiply both sides, you know, in order to cancel that. So basically I multiply by 2 inside. So I'll get 2x2 equals 1 minus 3i and 2.
So ready?
So is not it 1 over 2?
So it should be x2 by 2.
Okay. This is what I mean.
Yes.
Okay. Do you think it works?
No, Professor. Previous work.
It's 2x2.
But further previously, if we are having 2x2, then we just multiply inside, then it becomes 4.
Yes, it should be x2 by 2. Because we are
Why?
multiplying
Or we
inside
can
by
write it.
factors.
Okay. All right, guys, this is what we do. We basically, I take that, you know, C, when I do the scaling by factor 2, then we generally do this way. Okay. We just double the vector. Whatever the vector is there, I double that vector. Means, see here, I double this vector. So that's how we do scaling by factor 2. Okay, don't worry too much here. You can simply write, you know, some. You can also leave it just like this, but we'll be doing this a lot later on. So I just want you to remember that if we scale this by a factor of 2, that's how we do it. Anyway, so what we notice here is that for eigenvalue lambda equals 1 plus 3i, the basis vector, okay, the basis for eigenspace is given by this 1 minus 3i and 2. All right. So what I said is that you don't have to scale it, you know, you don't have to. If you are okay with this vector, then that's fine. You just copy this vector here. You don't have to do anything. But you need to know this, that sometimes calculation of when there is a fraction calculation is really tedious, especially in the next chapter we need it. So I just wanted to give you a heads up, okay? So this is our eigenspace, basis for the eigenspace. Now, according to the theorem we just seen, so by theorem 9 or whatever that number is the theorem 9?
11.
11, sorry, yeah, thank you. Okay, so by theorem 11, what we can write is that for eigenvalue lambda equals 1 plus 3i, which is actually the conjugate of the previous one. Okay, this is the conjugate of 3 plus 1 plus 3i. Okay, so for eigenvalue, this one, the basis must be the conjugate of this. The base for eigenspace is just the conjugate of that vector, which is 1 minus plus 3i and 2. That is the conjugate. That's it. You don't have to calculate for others. So that's the beauty of, you know, complex eigenvalues. So if the complex eigenvalue lambda equals 1 plus 3i and you calculate the basis for that, then another basis is just the conjugate. Remember in the previous section we had to do a lot of this work again. But in this case, once you find out what is the basis for the eigenspace, then another will be just the conjugate. So it reduces a lot of calculation. Any questions so far?
No, Professor.
Okay. Now, if you want to, you know, reduce it into esalon form, that's method 2. So method 2, I have given it here. So row reduce the augmented matrix. The whole idea is to reduce it into echelon form, but you know, whenever there is a complex number involved, reducing echelon form is not easy. It's not fun.
Very difficult, Professor.
Sorry?
It's very difficult looking like.
Generally, it's difficult, yes. For this question, it's not that much difficult, but for all the other examples, it will be difficult. Okay, so I leave it to you. I think you can handle it. It's just same thing. Only the thing is, it is a little bit complicated. Okay, I leave it to you. That's all about section 5.5.